Today we're going to talk about limits again, which we haven't talked about since chapter 3, and we want to talk about a new type of limit that we actually didn't see back in chapter 3, and that's a limit to infinity. Now if we're going to do that, it's been a little while, so let's review everything we know about limits. So when you're trying your limits, the first thing we always tried was direct substitution. And we had three possible things that could happen. So we said we're doing the limit as x approaches 10 of some function. So we plug 10 in for x. Now if you get a constant, like if you plug in 10 and you get 100, great, that's easy, that's the answer. The answer is 100, you're done and you move on. Now what usually happened was some of the other things. So you might have plugged in 10 and gotten 100 over 0. So we said, okay, well then our answer is either positive or negative infinity. That actually represents a vertical asymptote on the graph. Or maybe you plug in for 10 for x and you get 0 over 0. And that's the one we had to do extra work on. So today, what we're going to do, I told you it's a new type of limit. We're going to do the limit as x approaches not a number, but either positive or negative infinity. So it's not going to be the limit as x approaches 10 of something. It's going to be the limit as x approaches infinity of f of x, or the limit as x approaches negative infinity. So let's talk about what those mean. Let's start with the positive infinity. This is what it would look like. It looks like a regular limit, except, as I mentioned, underneath the LIM for limit, instead of x approaching some number, like 10 or 2 or 0, it says x approaches, and that's the symbol for infinity. So what it really means is it's asking you what's happening to the graph. It's not approaching from two directions anymore. See, our original limit, the one we did back in chapter 3, if I did the limit as x approaches 10, what you would do is you would find 10 on the x-axis, you'd put that dotted line there, and you would ask, what is the graph doing as it approaches that line from the left, and what is it doing as it approaches from the right? So it was two separate questions. Well, if x is approaching infinity, think about what that means. Here's my x-axis. Here's 1, 2, 3, 4, 5, 10, 100, a million. Infinity is as far as I can go this way to the right. So when you say x is approaching infinity, you're not approaching a vertical line. You're not approaching from two sides. You are saying, as I keep going that way as far as I can, just keep going forever, what is the graph doing? And you're answering questions like maybe the graph turns up, or maybe the graph turns down, or maybe there's a horizontal asymptote and the graph kind of flattens out against the asymptote like that. This is what you're looking for. You're looking for what's called end behavior, what's happening way, way, way off to the right. Now the limit as x approaches negative infinity of f of x is the exact same thing but on the left-hand side. So basically it's saying, again, if I'm thinking about my x values, if I'm approaching negative x, then I'm just going to the biggest negative number I can imagine. I'm going straight off to the left as far as I can and asking what happens there. So as I mentioned earlier in the notes, when you're evaluating limits, you always want to try direct substitution first. And that's where we run into a problem, because infinity isn't even a number. So what infinity actually is, it's the concept that numbers go forever. So if I say positive infinity, it's not like, oh, there's this number, infinity. What it means is numbers go forever. And no matter how big you make a number, if you add one to it, it's bigger. So there is no biggest number, but infinity is the concept of, imagine if you could pick the biggest number there was. So what that means, instead of plugging in infinity, what you want to do is just plug in a really, really, really big number and see what happens. So if you're doing the limit as x approaches infinity, say what would happen if I plugged in 1,000,000 or 1,000,000,000? If you're doing the limit as x approaches negative infinity, what would happen if I plugged in -1,000,000 or -1,000,000,000? So just again, pick that really, really big positive or negative number, plug it in and see what's happening. Now this is going to give us some new answer possibilities. So remember at the beginning I said you can either get a constant, you can get a constant over 0, or you can get 0 over 0. Well, now we're adding infinity into that too. So what you could get is either positive or negative infinity over a constant. So like let's say I'm doing my direct substitution and I realize I'm getting positive infinity over 10. That still just equals infinity. So infinity is such a big number that you can't change it by adding to it, subtracting from it, multiplying, dividing, anything like that. If I take infinity and subtract 100 billion, it's still infinity. No constant is big enough to affect it. Now, the one thing you do want to watch for is symbols. So let's say I got negative infinity over negative 3. Well, the answer is still infinity, but then you have to go, okay, well, it was a really big negative number divided by another negative number. It is now positive, so that would be positive infinity. So you still use the positive negative rules. Negative divided by negative is positive, one of each is negative, all that stuff. But just imagine infinity being a really, really big number. Okay, the second one, if you get any constant over either positive or negative infinity, it equals 0. So for example, let's say I'm doing my direct substitution and I come up with 103 over negative infinity. That just equals 0. Dividing by infinity, infinity is such a big number that if you divide by it, you equal 0. And really a good way to think of it when you're doing limits, you can kind of think of it 0 and infinity as reciprocals. If you take the reciprocal of 0, 1 over 0, that's essentially infinity. And if you take the reciprocal of infinity, 1 over infinity, that's 0. Now the last one is the one we're really focused on today. So let's say I get some combination, it doesn't really matter which ones are positive or negative. If I get some sort of infinity over infinity, that's a new problem for us. Just like before, when the 0 over 0 was a problem for us. So now we have infinity over infinity. And in fact, before I tell you what to do with that, let's group those two things together, because there's a name for them. If you take that 0 over 0 that was causing us problems in chapter 3, and the infinity over infinity, which is brand new, but is going to basically cause us the same problems, those are called indeterminate forms. And it means exactly what it says. It says can't be determined in this form. And that means you need to write it in another form where you can determine it. And if you think back to chapter 3, that's what we did. When we got that 0 over 0, we didn't just stop and throw the problem out. We said, okay, let's change it. Let's factor it and cancel this and turn it into something that we can solve. Same thing here. We're going to do that. If we get the 0 over 0 or the infinity over infinity, we need to work with it, manipulate it, and turn it into a different form, rewrite it so that we can solve it, so that we don't get that infinity over infinity anymore. Now, if you remember from chapter 3, when we were doing limits, I said, we're actually not going to spend a ton of time doing limits this way. I said, because once you've learned derivatives, there's an easier way to do it. And I'm going to teach you that right now because you know derivatives. So we're going to learn a way to do derivatives for the infinity over infinity, which also works for the 0 over 0. So if you go back to our chapter 3 questions, when you were getting that 0 over 0, those questions were kind of hard. They were kind of messy. I'm about to show you a much easier way to do them. It's called L'Hôpital's rule. It's a French name. It looks like it's spelled exactly like Les Hospital's rule, but that's not how we say it. It's pronounced L'Hôpital's rule, and it's a rule for using derivatives to evaluate limits. So here's L'Hôpital's rule. So let's say we're doing the limit as x approaches a, and a can be anything. That can be a number, or it could be positive or negative infinity, like our new limits from today. So the limit as x approaches absolutely anything of, now notice I wrote it as f of x over g of x, because in order to use L'Hôpital's rule, you have to get what we called an indeterminate form. You have to end up with 0 over 0 or some combination, doesn't matter where the pluses or minuses are, some combination of infinity over infinity. If that happens, then your original problem, the limit as x approaches a of f of x over g of x, equals the exact same limit as x approaches a again, but it's f prime and g prime. I took the derivatives. Now, I know when I present it as like how it's typed up in a textbook like this, it seems kind of strange. So let's put it into words. Let's make it a concept. So basically, if you're doing a limit question, you do your direct substitution, and you get an indeterminate form. You get 0 over 0 or infinity over infinity. Then what you can do, take the derivative of the top and bottom separately. And I underline that, that's very important. We're not doing quotient rule here. And that's why if you look back at the last slide, I didn't write it as the limit as x approaches a of f of x. Because you're not just taking the derivative of the whole thing. You're not doing quotient rule. You're separating. You're taking the derivative of the top, you're taking the derivative of the bottom, and then you're trying the limit again. And it ends up being a nice, easy way to do limits. You guys will see. So let's try out a couple examples here. Now this first one is actually a question from chapter 3. You can see just by looking, when it says the limit, it says limit as x approaches 3. So we haven't done our new ones for today. It's not the limit as x approaches infinity or negative infinity. It's the limit as x approaches 3. So let's try it out. Let's try direct substitution first. So I'm going to plug in a 3, and I get 3 cubed minus 19 times 3 plus 30. And it's all over 3 minus 3. And we definitely get a 0 on the bottom. That's easy to see. That would be 27 minus 57 is negative 30 plus 30 gives me 0. Okay, so we did get the 0 over 0. So I tried my direct substitution. I got the 0 over 0. It didn't work. Now, if this was chapter 3, I would have had to figure out how to do this question. Maybe try to factor it and cancel an x minus 3 and redo my direct substitution. It was kind of a lot of work. What we're going to do now is we're going to use L'Hopital's rule. So what I'm going to do, I'm going to leave the limit part. It's still the limit as x approaches 3. That part doesn't change. Now what I'm going to do is I'm going to take the derivative twice. Once of the top, once of the bottom. And I'm going to emphasize this again because it's very important. We're not doing quotient rule. We're not taking the derivative of the whole function as one thing. We're separating it into two parts and taking each derivative separately. So if I take the derivative of the top, it's going to be power rule. Multiply by 3, lower the exponent by 1, I get 3x squared. Then the derivative of negative 19x is negative 19. And the derivative of 30 is 0. We can lose that. And on the bottom, the derivative is just 1. The derivative of x is 1, and the derivative of negative 3 is 0. So I don't even need the over 1. Basically what I have is the limit as x approaches 3 of 3x squared. Oops, I don't need those parentheses yet. (3x squared minus 19). Now, try direct substitution. It has to work. We don't even have a denominator anymore. You can't get 0 over 0 if you don't have a denominator. So now, if I do direct substitution again, plug in 3 for that x, I get 9, I get 27 minus 19, I get 8. And that's it. That's the answer, is 8. So basically, the beginning of the question in blue, same as chapter 3. I tried direct substitution, I got 0 over 0, something was wrong. Now, instead of having to factor or whatever we did with, simplifying radicals or whatever, I just took the derivative. I did the derivative of the top and the derivative of the bottom, and I tried L'Hopital's, I tried limits again, direct substitution. All right, let's do a new one though. Let's do an infinite limit. So here, what we have is one of our new limits. The limit as x approaches infinity of x squared minus x over x squared minus 1. So let's say we do this. Now, I'm going to write this out as if I were actually doing direct substitution. So let me kind of imaginarily substitute the number infinity in. So I would have infinity squared minus infinity over infinity squared minus 1. Now, the bottom is easy. If I take my really big number infinity and square it, it's even bigger. It's an impossibly big number. Subtract 1, doesn't even matter. It's still this huge number. It's bigger than my original number, so it's definitely infinity on the bottom. Now the top is where some people might get confused, because they go, okay, well, infinity squared is still infinity, and infinity minus infinity is 0. It cancels each other out, just like x minus x is 0. And that's not true. So that's where infinity gets a little confusing. Infinity is not a number, and it doesn't cancel. Infinity minus infinity doesn't equal 0. What you have to do is decide which infinity is bigger. So remember, we imagined ourselves taking this really huge number, like 1 billion, and putting it in. If I take 1 billion and I square it, it's even huger. So this really big number. Then you subtract the other number, 1 billion, it seems kind of small compared to our new number. So basically what we have here is we took our original number infinity, we squared it, which made it even bigger, we subtracted off the original amount, it's still this impossibly large number, it's still positive infinity. So that's the tricky part of this, is you guys getting used to working with infinity, even though it's not a number, it's a concept. And you can have more than one infinity in a problem, and one of them can be much bigger than the other. So there's this rule where basically what you can do if you're dealing with powers of x like this, it's called the principle of dominance. It says if you're dealing with powers of x, really only the highest power matters. If I have an x to the 10th power and an x to the 5th power, if I'm doing the limit as x approaches infinity, you can just kind of ignore that x to the 5th, because the x to the 10th gets so big that everything lower than it becomes insignificant. So try to focus on that. It takes a little while to get used to. At first, it might seem weird for you guys. You might miss a few questions at first, but the more you try it and the more you get used to it, you'll get comfortable assuming infinity. But the idea for the question, an infinity over infinity is like a 0 over 0. We need to find a way to do the answer, and I'm going to do L'Hopital's rule again. I'm going to do it the exact same way we just did. So let's leave the limit part. We have the limit as x approaches infinity. And then let's take the derivative of the top and the bottom separately. So on the top, the derivative of 2x by power rule, or I'm sorry, the derivative of x squared is 2x by power rule. Multiply by 2, lower the exponent by 1. And the derivative of negative x is negative 1. Now on the bottom, the derivative of x squared is 2x, and that's actually going to be it. The derivative of negative 1 is 0, it disappears. All right, so let's try our direct substitution again. And just, again, I don't usually show my work this way, but for the notes, we have 2 times this really big number, minus 1, and it's all over 2 times this really big number. So I took my big number, I multiplied it by 2, it's even bigger, subtracted 1, not a big deal, definitely positive infinity on top. And then on the bottom, I took my really big number, multiplied it by 2, it's even bigger, definitely still infinity. So I tried L'Hopital's rule, and I got infinity over infinity. That doesn't mean it didn't work, it means you need to do it again. So sometimes L'Hopital's rule works like a chain. Like you'll start with an infinity over infinity, you'll do L'Hopital's still infinity over infinity, do it again, do it again, do it again. Finally, you get something that's an answer. So let's try it again. Let's leave the limit part. Limit as x approaches infinity. Now on top, the derivative of 2x is 2. The derivative of 1 is 0. And on the bottom, the derivative of 2x is also 2. Now all of a sudden, there's no more x's. if there's no more x's, there's nothing to plug infinity for, and basically whatever's left is the answer. So the answer to this question is 2 over 2, which is 1. So the final answer to this question is actually just the number 1. We did get an answer for it. We don't have to plug in any more infinities because all of the x's end up canceling out. So that's how L'Hopital's rule works with an infinite limit. The tricky part isn't the derivative part. The tricky part is realizing what happens when you substitute basically infinity, some really, really big number. So here's a complete list of possible limit answers. Remember, I gave you those 3 earlier. And this is for every question. It doesn't matter if it's a chapter 3 question, where the limit as x approaches 7, or the one we just learned, the limit as x approaches negative infinity. These are your possible answers. You could get a constant, like the one we just got. The answer is 1. You could get a constant over 0, which is either positive or negative infinity. And you could get a 0 over 0. That's chapter 3 right there. Well, the ones we just added to it, you could get infinity over some constant, which equals infinity, and that could be positive or negative there. You could get a constant over infinity, which equals 0. Divide it, remember, and I said the best way to think about that when you're dealing with limits, just think of 0 and infinity as reciprocals. 1 over each one becomes the other, or any constant over each one becomes the other. And then we have the plus or minus infinity over infinity. Now, number 3 and number 6 on this list, the question marks, those are the ones that need more work. And even though we learned some ways to do it in chapter 3, I would say from now on the best way is L'Hopital's rule. So if for any limit question you ever get 0 over 0, or any kind of positive negative infinity over infinity, take the derivative of the top and bottom separately and try it again. If you keep getting 0 over 0, or if you keep getting infinity over infinity, keep going until you get an answer. And the answer will be one of those 4 on top. It'll be number 1, 2, or 4, 5.